What is something that cell transport, gas separation, and water filtration all have in common? These processes all involve some sort of mass transport through a membrane. In order to separate molecules or compounds, there has to be differences between the substances that you are trying to separate. Membranes are one of the methods that are able to inhibit or allow the movement of specific molecules in order to cause different rates of mass transfer through the membrane. This is achieved by using specific membranes designed for allowing certain molecules to pass through them based on criteria such as the size of the molecule. And these membranes are called semipermeable membranes due to their ability to only allow some molecules to pass through them. This concept can be seen in the example showing gas separation, as well as diffusion of certain molecules through the cell membrane. We will demonstrate this concept using a simple iodine and starch experiment. A solution of potassium iodide and iodine, also known as Lugol's solution, is usually dark yellowish brown in color. However, it is a starch indicator, meaning that a reaction occurs when the solution is exposed to any type of starch, resulting in a dark purple color, which can be seen in the video where the iodine solution is mixed directly with a solution of cornstarch and water. However, there is a difference between the molecules of iodine and molecules of cornstarch, which is their size. We could show this difference by using dialysis tubing as a membrane to separate a solution of cornstarch and a solution of iodine. Dialysis tubing is a type of semipermeable membrane that only allows molecules that are small enough to pass through them. When used in this specific setup, you will be able to see how the size and concentration of solutions on both sides of a membrane affects the diffusive mass transport through it. To set up our experiment, we will need Lugol solution. We used a concentrated solution of 4% potassium iodide and 2% iodine, which will be diluted further in our experimental setup. We will need a beaker to perform the experiment, as well as dialysis tubing for the membrane, water, and cornstarch. To make the starch solution, we mixed 3 grams of cornstarch with 100 milliliters of water and mixed well. Then we poured the solution into the tied-off dialysis tubing. To make the potassium iodine solution, we mixed 40 drops of Lugol solution with 350 milliliters of water in the 400 milliliter flask. This diagram is to show the expected outcome of our experiment. As time passes, the iodine solution is expected to travel through the dialysis tubing, while the starch remains inside the tubing. As the iodine molecules travel into the tubing, the starch will react to it, turning a dark purple color. Here are the before and after images of our first run of the experiment, where the dialysis tubing was inserted into the iodine solution vertically. The picture on the left shows our experimental setup before our experiment was run. You can see the white mixture of cornstarch and water inside of the steel dialysis tubing, as well as the dark yellowish iodine solution inside of the beaker. The picture on the right shows the result of our experiment after it was run for 15 minutes. The cornstarch solution inside of the dialysis tubing has turned a dark purple color, indicating that the iodine has diffused through the membrane, therefore mass transport of iodine has occurred from the beaker solution to inside the dialysis tubing. However, there is no mass transport of cornstarch from the dialysis tubing to the beaker solution, as there is no reaction occurring outside of the tubing. A few things to note on our experimental setup is the darker area at the bottom of the flask containing a higher concentration of iodine. This was due to insufficient mixing that resulted in an uneven concentration gradient of iodine. After transport has occurred, the bottom of the dialysis tubing shows a darker purple color, which indicates that there was more mass transport occurring in this region. With higher concentration, mass transport occurs at a faster pace. Here you can see a sped up version of our reaction happening over a 15-minute time period. Note that the change in color happening inside the tubing but not outside. This is a visual representation of the vertical tubing inserted into the iodine solution. Due to the iodine solution having a higher concentration at the bottom of the flask and the dialysis tubing having a high concentration of starch at the bottom, which is due to cornstarch not being entirely soluble in water, the transport occurs quite rapidly at the bottom and slower at the top of the tubing. Here shows the before and after images of our second experimental run, where the dialysis tubing was inserted horizontally. It should be noted that the iodine solution was allowed to reach an equilibrium in which concentration of iodine was uniform through the flask. This led to the dialysis tubing having a more uniform dark purple color, meaning the transport occurred more evenly. You can see a sped up version of our second experimental setup happening over a 30-minute time period here. This image represents the horizontal dialysis tubing submerged in the potassium iodide solution. As time passes, the iodine travels through the membrane of the tubing, which was visually shown with a dark purple color change inside of the tubing. This occurred more uniformly due to two factors, one being that iodine was more uniformly distributed, the other being the cornstarch was also more evenly distributed inside the tubing. As this experiment demonstrates, membranes are an effective way to selectively allow the mass transport of specific molecules. Chemical engineers can take advantage of the effectiveness of semipermeable membranes in combination with other physical phenomena to effectively separate specific substances. Membranes can be used with concentration differences to drive diffusion, but the driving force of separation can come from temperature differences or temperature gradients, such as in membrane distillation, or pressure differences caused by gravity or by pumps, such as in membrane filtration. Although the concept of semipermeable membranes is very simple, it has a large variety of applications that chemical engineers can use.